Welcome, ladies and gentlemen, to this video lecture. So in discussing our previous example, we came across a claim that I made, and let us actually prove this claim. It is a nice exercise. So I'm going to call this a lemma. Remember, what is a lemma? A lemma is just a small independent proof that you use to do something else with. So it's a small tool that you use to do something else with. And what did we use it to do something else with? We used it to decide the behavior at plus and minus infinity of the function that we considered in our previous example. Okay, so I am going to prove this lemma. So first of all, what have we got? We take a continuous function defined everywhere, and we define big F as the integral from 0 to x of f, little f of t. And now the statement of this lemma is if the limit of little f as x goes to plus infinity, if the limit of little f is plus infinity, then the limit of the big F as x goes to infinity is also plus infinity. Okay, so let's prove this. Okay, so we want to prove if this holds, then that holds. So we want to assume that the limit as x goes to plus infinity of little f of x is equal to plus infinity. So we are assuming that this holds. So remember, this is a shop, and we can, if we bring in any capital E, as long as it's positive, this shop will sell us some other positive number which does something. So what I'm going to do is I'm going to use 1, which is a positive number, and I'm going to buy an M which does something over here. So so let's write here by this assumption there exists an M bigger than 0, so that if x is bigger than M, then f of x is bigger than 1. So if you think about the definition of what this statement actually says, it says for any E there exists an M, but now all that I'm doing is I'm choosing the E to be 1, and I'm taking this 1 to the shop and I'm buying an M, so that beyond this M, our little f is always bigger than 1. And you can think of why this should be the case. So our little f goes to plus infinity, and since it goes to plus infinity, there must be some point M here, so that beyond that point our function values always lie above the horizontal line at height 1. Okay, so now now we see, how is f defined? How is f defined? Is the integral from 0 to x. So if we now think about it, is the integral of little f from m to x is big F is defined as the integral, if this is the graph of little f, f is the integral of little f up to x. But beyond this m, we see here the graph of little f, or the function values, is always above 1. So we can force for any given number, we can, by taking a point far enough, we can always force this area to be as big as possible, because it always, or let's say the area below the graph, always includes this rectangle here, which has height 1. So if we make the width but big enough, then we can force capital F to be as large as possible. Okay, so now what do we want to prove? So to prove the limit as capital F as x goes to plus infinity is equal to plus infinity. That is what we want to prove. Now, remember, this means something very specific, so I'm going to write out an outline for our proof. So this statement says for any capital E there exists, so we must define it. So define, I'm going to use a different symbol, n, as something, but it must be positive, so that if x is bigger than n, so assume x is bigger than n, and now what do we want to do? We want to show that f of x is bigger than e. Okay, how will we do that? So I'm going to write it down here. So f of x, that is defined as integral from 0 to x of little f t dt. And now let's split up this integral as the integral from 0 to m. And what is this m? This m is the point beyond which f of t is bigger than 1. And 0 to x of f of t dt, but beyond this point, no, actually not from 0, from m. So, but beyond, so from m onwards, this integral is, or the integrand is always bigger than 1. So we get 0 to m f of t dt plus integral from m to x f t dt. Oops, that is 1. And this integral is easy to compute, 0 to m f of t dt. What is this? This is equal to x minus m. Okay. Let us write this together. Minus m plus x. And now we see here, if our x is big enough, we can make this expression as large as we want. So let us think, what do we want? We want, so I'm just going to do it down here. Remember, what do we want? We want this expression to be bigger than this e that we fixed. And So we need to define an n so that beyond that n, this expression is bigger than e. And we have control over n. We can choose the n freely, and we are making this assumption that n is that x is bigger than that n. Okay, so let us think about what do we want. So I'm just gonna put a line there, and this is just a little bit of rough work that we're doing on the side. This thing we want to be bigger than e. So we want to know, we want to choose our x to be bigger than something. So x should be bigger than e minus 0 to m f t dt plus m. And we see if we choose our x to be bigger than e minus that plus m, then we see here that here a whole bunch of these terms will cancel, and we will be left with an e. So, and what are we going to do? We're just going to define n to be that. So define n to be e, and we see here we are using e, and minus integral from 0 to m of f t dt. So this is a constant. Where does this m come from? We have previously defined it. It comes from choosing or it comes from using our assumption here. So this is just a constant, and plus m is the last one. So we define n as that, and we assume x to be bigger than capital N. So therefore, what do we have here? And let us continue here. So now this x is bigger. So we have these terms which do not change. And this x is bigger, is assumed to be bigger than n, and n is e minus ft dt plus m. That m cancels with that one, this term cancels with that one, and we are left with e. And there we have verified that this limit, the limit of big F as x goes to infinity, is equal to plus infinity, under the assumption that the limit of little f as x goes to infinity of plus infinity. Okay, so there we have actually proven it. So I will leave as an exercise the other claim that we made looking at our previous example. Exercise, prove the other claim. Okay, I will see you in the next one.